Hi. So today in AP Chem, we're gonna be doing notes and homework 16, which is on solutions, which is something that I did. I'm pretty sure the other chemistry teachers did last year as well. But here's the thing. This set of notes is really, really long. We've got page 1, page 2, page 3. Literally so many pages. Page 4, 5. That's just the notes. 5 pages of notes. This is an extended like a homework problem, and I just gave you lots of space to do it. And then there's the actual homework. So this will definitely be broken into multiple videos, and I might jump around within note 16. So there's kind of the overview. So flipping my camera, I have here some just some scratch paper. Reminder that the 3 states of matter that we work with are solid, liquid, gas. And then in AP Chem, we've got another one. It's not really a state of matter. It's just an extra, I don't know what to call it, classification. So solid's pretty straightforward, right? Like we talked about that, I think in notes 14. We said that there's the 4 types of crystalline solids, and gas is the one that we just got done doing, note set 16. Or sorry, note set 15, because I think, yeah, today is 16, so this must be 15. Liquid, we actually don't like do it all in AP Chem, so cross that out. But students generally get confused between liquid and aqueous, and they're definitely not the same, because liquid would be, for example, if I took sodium chloride table salt and I heated it up and had nothing else in it, just heat, it would turn into like molten lava looking sodium chloride. That would be liquid NaCl. We don't really deal with that. But if I were to take the NaCl instead and add it to water, then that would take this ionic compound and potentially it could dissolve into its ions again. The key word being dissolve. So do not get these two confused, because notes 16, what we're doing today, is about aqueous solutions. The root word of all of this is SOL, like dissolve or solution. So we're going to be dealing with that. But that's what an aqueous solution is when it's dissolving. So here's a YouTube video you can look up. Will molten salt melt lead? And let's play. I want the sound off though. I don't want to listen to it. Okay, so literally you can see it's just table salt getting dumped in. And he's got this really cool rig. I don't remember what this is called. I don't remember. Anyway, usually it's used for like making weapons and stuff. And I don't even know how he's able to put the camera like over the top of it, because it gets so hot. And then make my face a little bit smaller here, maybe. Whoop. So here we go. There it is. It's molten. That is the sodium chloride, and it is just so hot it has melted into a liquid. That is not what we're dealing with, but it is kind of interesting to watch. So he pours it on the metal, and I don't know why he's doing this, just for fun, I guess. But he kind of shows that it is so hot that when you put like pieces of lead shot, the little balls on top, like, and he stirs it here, it melts the lead. So he's basically turned everything into lava by just heating it up so much. And then here's the lead pieces on the bottom side and our big salt pancake. Gross. Gross. Okay, so there's that video. But that is not what we're working with solutions. I just thought it was cool. So let me show you the other video on what we're more so dealing with. So again, I don't want to listen to this guy talk, but what he does is he's like, his like setup looks so cool. Like, check this room out. I'll be on this shelf here. He got like microscope, dead bird in a box, another one, some spiders, like, oh, it's so cool. He just has like the coolest stuff. I have one of these bamboo plants, so I'm half cool. Rubik's Cube, classic. I don't know, it just looks cool. So anyway, he's got his setup here, and he has water, 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 water in all the beakers. And then in front, he has different solutes that he's going to put into the water and see if they dissolve. So he'll actually label them here when he puts them into the video or into the water. So I'll scoot my face out of the way. So dump, 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 puts in a little bit. And the idea here is to show like what it means to be soluble and what is not soluble. Not everything is soluble in water. You're very used to a life where everything dissolves in water, like salt. You know, you can put it in there and it dissolves. Sugar, same thing. Look, where did it go? Chalk. See how it's not dissolving? It's just like getting wet, but it didn't dissolve. Starch, and then baking powder. So he stirs them all, lets them sit. And then after a few minutes, you can see this was the salt on the left. That one definitely dissolved. It looks like we've got a clear thing going on. What was this one? Sugar also dissolved. Chalk did not. What was this last one? Let me go back. Baking powder did not. And then I wish they were labeled like right here. What was the last one? Oh, sorry, baking powder did. Starch did not. Starch did not. Okay. So starch and chalk did not dissolve in water. And there's our final picture. So that's what we're working with today. We're dealing with solutions, aqueous solutions. Does it dissolve and make a solution or not so much? So here's the very, very first page of notes 16. Noises. Okay, so basically, we're taking a powder usually, and we're mixing it into generally water, and then we're seeing if it dissolves. So where do I want to start this? I want to start this here actually with molarity and concentration. So the easiest solution for me to kind of think about or visualize is Kool-Aid. Kool-Aid is a solution. The solute would be the actual powder, the Kool-Aid powder, the sugar crap that you're scooping in. And the solution itself would be the Kool-Aid drink when it was done, the final product. So solute mixes with solvent. I don't know that that word is listed anywhere, but the solvent when you make Kool-Aid would be the water. Solute powder plus solvent water equals solution Kool-Aid drink. And we use molarity to determine the concentration. Because it's one thing to say, like, yes, this Kool-Aid is oh so concentrated, but like, that's fine for Kool-Aid, but you can't just go around the chemistry lab being like, oh yes, these chemicals, let's see. Oh, like, and then you die because you're not supposed to do that. Plus, we don't even have the ability to like numerically describe like, oh, this is a 3.25 concentration right here. Like, we don't have that ability. So mathematically, we need molarity to determine the concentration for us. So what we're going to do is to get molarity, which is abbreviated capital M, we're going to take the moles of the powder and divide it by liters of the solution. Cool. So quickly, we're going to flip over here to homework 16 that goes with this set of notes and jump to number 2 where it says calculating molarity. The problem says determine the molarity of a solution that contains 1.22 grams of potassium iodide, Ki, dissolved in water to make 250 milliliters of solution. So I'm going to take this formula, molarity equals moles over liters, copy, paste it right here into the homework. Molarity equals moles per liter. I do not have either. I do not have moles. I do not have liters. I guess we just give up, kids. That's it. End video. Bye. Have a good rest of your class. Can't do it. See ya. If only. Okay, so moles. We can get moles by converting the mass into moles. If only there was a way to convert mass into moles, maybe using the molar mass. Cool. So we gotta get our periodic table out. Actually, hold on a second. I'm at home. I can do this really cool thing. Okay, Alexa, volume 7. Great. Alexa, what is the molar mass of potassium iodide?
Potassium iodide's molar mass is 166 grams per mole.
Thank you. I love being at home. Okay, so she just told me that. But you could look it up, add up a potassium, add up an iodide. Now we have that. And to convert this, let me do it over here on the side. .22 grams of potassium iodide, 166 grams per mole of potassium iodide equals 0.007349 moles. Cool. We're going to plug that in here. And liters We have 250 milliliters, but that's not quite what we're looking for. We need liters. There's 1,000 milliliters equals 1 liter. So math. 0.250 liters is the same thing. So to get my final answer here, molarity equals the number of moles I had divided by the number of liters final answer, the concentration of this solution is 0.029 molar. That is its concentration. So it's really not hard. You just have to get moles on top of liters, but you might have some additional calculations where you go from grams to mole or milliliters to liters, things of that nature. But essentially, it's just taking that fraction and getting an answer. But again, it works better than just trying to like taste it and being like, this is 0.029 molar for sure. Got it. Like, can't do that in the lab, and I can't even do it at all or even my drink. Okay, so there's that. The next thing on the page here, back to the notes, is dealing with dilutions and how do we make something more diluted. Diluted is the opposite of concentration. So I'm going to use two different colors of green. I'm going to use dark green for the concentrated stuff, and I'm going to use light green for the less concentrated stuff. This is like the kiwi Kool-Aid that's like actually good, and this is the kiwi Kool-Aid that your grandma made and put in too much water and it's gross and diluted. So the formula for dilutions over here is M1V1 equals M2V2. We're taking the molarity of solution 1, which I'm calling concentrated, the volume of solution 1, which I'm calling concentrated. You add water, and we're trying to figure out, now that it's got water in it, what are the molarities and volumes now that it's been diluted? Still the same exact solution in identity, green, green, but I'm adding water to make it more watery. So dilution equals adding more water to make a solution less concentrated. Diluting with water, sorry, that should say diluting with water. Diluting with water does not change the number of moles present. That makes sense, because zooming in, crunchy noises. Looking at the picture here, if I've got 1, 2, 3, 4, 5, 6 particles in there, the water line is coming to here. I add water, now the water line is still here. Adding water didn't change the fact that I still have 1, 2, 3, 4, 5, 6 particles in it. It's just going to make this one be less concentrated. Concentrated. I need to concentrated on spelling that word. So this formula isn't hard at all. So let's do a problem from the homework using this formula. M1 V1 equals M2 V2. Copy, paste into homework 16 number 4. How would you prepare 100.0 milliliters of a 0.40 molar solution of magnesium sulfate from a stock solution? Stock means concentrated. It means you went and bought it from a store that had it in stock. It's kind of like bulk. Okay, from a stock solution that is 2.0 molar in concentration. Okay, so originally it was very concentrated. It was 2.0 concentration. So I'm going to make that dark green. And I'm trying to prepare it down to be 0.40. For whatever reason, I don't need it that concentrated. I only need it this concentrated. And I only need to make 100 milliliters of it. Formula, M1V1 equals M2V2. M1V1 equals M2V2. Dark green over here, concentrated side. The molarity of the concentrated is 2.0. I don't know the volume of the concentrated. I guess I need to figure that out. So let's use X as my variable. Equals molarity times volume. The volume is 100 milliliters. I probably should have labeled all of them, but I'm not super worried about anything other than if milliliters is what I use for the volume here, then milliliters will be the volume on this side. They have to match. So solving for X, 0.40. Let's see. 0.40 times 100.0 divided by 2.0, dividing it across. X equals 20 milliliters, since the other side was in milliliters. So that's my answer, but that doesn't actually answer the question, because it says, how would you prepare this from this? So if I was to write it out, I would more so say, measure out 20 milliliters of the 2.0 molar and then I measured out this much of the concentrated, but I'm trying to get it to be 100. So I would measure out this much and then add, I guess I would be adding 80 milliliters to get it to be 100 total. So if this was my little beaker and I want 100 milliliters of it, I would put 20 milliliters of the concentrated in, and then fill the rest with water. until I reached 100 milliliters. We're not adding 100 to that because then it wouldn't be the right concentration nor the correct volume. Add in the 20, fill to 100. In this case, that's going to mean 80 of water. How much water would you add to 25 milliliters of 1.00 molar NaOH to change its concentration to 0.75 molar? So pause the video here. You try it, figure out how much water would be here. This should take you probably less than a minute, but put 2 minutes on the timer and then unpause once you're done. But since I am recording the video, I don't have to pause nothing. So let's see. Equals 2 B2. How much water would you add to, I have 25 milliliters of the concentrated. So I'm getting that X equals 33, but that's not how much I'm adding. That's the total volume. 33 milliliters of the 0.75 equals 25 milliliters of the 1. But I already had 25. So to get from 25 to 33, I'm going to, I should have done it the other way. I'm going to need to add 8 milliliters. Ish. This isn't how much I'm adding. It's just saying that 33 here, that this all equals itself. So how do I get to 33 from 25? Okay, and somewhat back to the notes. There was just this little teeny bit that I skipped that I shouldn't have. I just didn't see it. Ionic compounds dissociate in solution, okay, like water. And what they're going to do is multiply the molarity by the number of ions present. Sounds difficult, but it's not tricky at all. This is on the homework number 3 that was skipped in the middle here. So if I had a solution of BaCl2, barium chloride, my concentration is 0.25 molar. But this, we're assuming that it dissolved fully. When this breaks apart, I get 1 barium and I get 2 chlorines. So if the original concentration was 0.25, then I'm going to say my final answer here, I'm still going to have 0.25 molar of the Ba2 plus, but since I get twice as much chlorine every single time it breaks apart, 0.25 times 2, math, I'm getting 0.25 0.50 molar of the Cl minus. The chlorine, there's twice as many of them, so it's twice as concentrated. Don't overthink it. Like, I don't know why, but students have a hard time with this, and I'm just like, I don't know how, as clear as I can make it. Like, we've got K3PO4. Got 3 potassiums, and PO4 is a polyatomic that stays together with the 3- charge. I had 0.1 of the whole thing. So every time this breaks apart, I get 3 of those, 1 of those. I'm going to have 0.33 molar concentration of this, 0.11 molar concentration of this. So don't get too hung up on it. It's just saying that if you have twice as much, or sorry, 3 times as much potassium, the concentration will be 3 times as much. Duh. Okay, so there's the little first bit of the homework. Now let's make this obnoxiously difficult. Let's say that, where do I want to start this? Not all things dissolve in water. So there are rules on how to decide which things do and don't dissolve in water. So I go to Google and I typed in solubility rules, rules for what's soluble and what's not. And here's my screen share. Usually you'll get either a table like this that has rules, or you'll get, I like this one from Flynn. Not really. Oh yeah, here we go. Okay. So I like this one because you can say like, what's the compound and see if it would be soluble or not. So on the one that we just did in the homework, we had 3A, we were looking at barium chloride. So on my chart here, here's barium and chloride down here. I find the intersection, barium chloride soluble. Sweet. The other ones we had, potassium phosphate. So here's phosphate. Here's potassium. Yep, that one was soluble too. And the last one, I don't think chromium's on this chart. Nope, it's not. So I'm not even going to try. But all of the different values here, green SOL is soluble, red INSOL insoluble, and SL slightly soluble. So here's what's weird though. I don't know if you can see on your end, but it's got these values down here at the bottom. It says that soluble means that we were able to get more than 1 gram of the powder to dissolve into 100 milliliters. That's our definition for, yes, you are perfectly soluble. You can scoop 1 gram into 100 milliliters and ding, dissolves. What we're saying is not soluble is less than 0.1 gram into 100 milliliters. And anywhere in between that, from 0 to 1, pretty much grams into 100 milliliters is slightly soluble. So that's going to be kind of tricky. You do not need to memorize this chart though. My first year teaching AP Chem, I was like, memorize this chart. But as I've taught more and more and learned some more tricks, let me show you instead what you need to be able to do on your AP test. It's a lot less work. So here's the cool trick that I always use. There's really only a couple of things that you actually need to memorize, and they're right here, A and B. All nitrate salts, nitrate is NO3 with a 1- charge, polyatomic, you should start remembering those. All nitrate salts are soluble. All salts containing 1+ ions are soluble. So like Na1+, potassium 1+, NH4, this is ammonium, another polyatomic. 1+ are soluble. Everything else, the problem that it gives you, it'll have to tell you if it is soluble or not. It'll have to specifically give you data. Memorization of the solubility rules other than those above, these two, will not be assessed on the AP exam. So we're going to deal with this more later, but keep that in mind. These are the two rules that you actually do need to memorize. Water, the common solvent. Water can dissolve ionic compounds because the cations, the positive ions, are attracted to the oxygen end of water because oxygen has this partial negative because it's electronegative and pulls the electrons towards him. Anions, the negative ions in things, are attracted to the hydrogen ends over here that are slightly positive or partial positive. So zooming in, zooming. I'm going to pause the video and color this so I can show you. Pause, click, you don't have to pause it, just me. And Shazam, I colored it. So here's what's cool. Sodium chloride, NaCl, Na, let's see, I'm going to color these different. Na is a cation, it's positive. It's in the 1+ column on the periodic table, there it is. And that positive charge is like, hey, super attractive looking to all of the partial negative on the water. So the water goes oxygen end first to try and maximize its interaction between the plus and the partial negative. Whoa, that's an IMF. Woo, Miss Oliver, I remember. Maybe you do, maybe you don't. IMFs, specifically, this is an ion dipole intermolecular force because there's our ion. Water is polar, so we've got the positive and the partial negative having an interaction. That is why it dissolves. Chlorine is the other part of this. Chlorine is negative, Cl minus, in the -1 column of the periodic table. And since he's negative on the inside, he's attracting all of these partial positives that are on the hydrogen end. So this is still ion dipole, but now we've got negative and partial positive that are like, woo, IMF. This is how water dissolves ionic compounds. Okay, and I'm going to show you this really great video from, goodness, the 1700s. Share sound, yes, I would like to share sound. Optimize screen for video clip. Yeah, let's do that. Okay, so here's my screen share. And let's see.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Wow, that was beautiful. So beautiful. I am going to screen share again though, and not share the sound because I just want to talk through it. And have my face on the screen. So here's what's cool. So like, well, why are you still talking? Stop talking. Notice they're coming in hot, like little hydrogens on that side. Oh, but flip it around. Notice the oxygens are now coming in. So it just changes the orientation of your ion dipole intermolecular forces. Whoop. So on this side, red coming in, but over here on this side, we've got white coming in. I wish they'd use like different colors because I feel like the white in this kind of looks like the hydrogen in the water. We should have had multiple colors. When you guys are super adults, and I know some of you are going to work in graphics and visualization and media and stuff, there is big bucks to be had if you were able to make simulations and visuals for chemistry, because chemistry is a very abstract subject. It's not like physics where we can always like, watch this, whoop, whoop. Like we have to visualize a lot of things through simulations because doing it in the lab with chemicals doesn't quite cut it for looking at what's happening with the specific molecules. So if you want big bucks and all of my love and affection, you should go into simulations for chemistry. Okay, switching back here now. So that's kind of almost the end of this. Polar substances can also dissolve into water because of instead of having an ion dipole attraction, polar molecules can interact with polar water through dipole interactions. Okay, and that's where I'm going to pause the video here for 1 second. I'm going to stop it for today. I don't want each video to be too long. And we'll pick up there in the next one.